The problem statement from GATE Physics 2016 reads as follows. For the digital circuit given below, the output X is. We have been given a circuit with 3 logic gates, and we are required to find the output X, which is on the right side. The 3 inputs are A, B and C, and we have been given 4 options. This is a multiple choice question with only one correct option, and we have to choose the correct option. This slide shows the different logic gates that we typically encounter, so namely NOT, NAND, AND, OR, NOR, etc. Along with their algebraic expression in the second row, you can see it here. It is so NOT is represented as A bar, AND is represented as A times B. Similarly, NAND is represented as A times B. So note that A and B are the inputs here for each logic gate. These are 2 input logic gates. So the inputs everywhere are A and B, and the output we are depicted as X for each of these logic gates. So the output is X, right? So these are the symbols that you can see. Typically a NAND, I'll try to go through a NAND symbol. So NAND symbol is nothing but an AND symbol, which is this symbol that you see, followed by a circle at the vertex. This circle denotes a NOT. So you can see that we have just borrowed this NOT. So if you combine these two, and followed by a NOT, what we get is a NAND. So this is what a NAND circuit looks like. And also this is the truth table for a NAND gate. So let's just go through the truth table. For one, truth table is nothing but we list first on the left side, we list all the possible combinations of inputs. So for instance, here we have 2 inputs A and B. So the possible combination is, since this is a binary logic, so A can be 0, B can be 0. This is the first combination of A and B. Second, A can be 1 and B can be 0. The third possible combination is B is 1 and A is 0. And finally, the last combination is A is 1 and B is 1. Now, how do we find the output? We find the output because we know that X is equal to A times B whole bar. So if I times A times B, so A times B, 0 times 0 is 0, and I take a bar of that, so the inversion of 0 is 1, so we get output as 1. Second, again, A times B, so A times B is 1 times 0, so 1 times 0 is nothing but 0, and we take a bar of 0, which comes out to be 1. Similarly, again, A times B, A is 0, B is 1, so 0 times 1 is 0 again, times, and we take an inversion of that, we take a bar of it, so it comes out to be 1. Finally, A times B, which is 1 times 1 is 1, and we take a bar of it, so it comes out to be 0. Hence, that is how the truth table is obtained. I just went through the truth table for a NAND gate. Using similar argument, the truth table can be obtained for each of these logic gates, and for that matter for each even complex combinatorial circuits. This was the problem that was given to us. So we had a NOT gate at the top, we have an OR gate at the bottom, and we have a NAND gate at the right. I've identified these gates because you see these here. So just based on how do they look like, we can identify them, right? So now let's just first look at the top NOT gate. So if you look closely at this NOT gate, the input to this NOT gate is A. And we know that the output expression for the NOT gate is nothing but the inversion of whatever is being provided to it. So you can see that in this case. So for NOT gate, the output is nothing but, this is the output. So output is nothing but input, the bar of input. So if I see it here, so the output would be nothing but the bar of input. The input is A to this NOT gate. So the output would be A bar. Similarly, now if you look at in the orange rectangle, you see an OR gate. This is an OR gate. So what does OR gate do? OR gate sums. So the output here would be the sum of the 2 inputs. So the 2 inputs are B. So I'll write plus symbol here first, and the 2 inputs are B and C, right? So the output for this OR gate would be B plus C, correct? Now finally look at this green rectangle. So the green rectangle is nothing but a NAND gate, right? And what is the output of a NAND gate? The output of a NAND gate is, let's say, whatever the input you are providing here, and let's call this input P, and let's call this input Q. So the output X for this NAND gate would be P times Q and then a whole bar of it. P times Q whole bar. This is what the algebraic expression for a NAND gate looks like. Now note that P is equal to A bar. P is nothing but this is a wire here. So the value of P, so we know that, now we know that P equal to A bar. And we also know that, look at Q. Q is nothing but the output of this OR gate here, which is B plus C. So I can write and Q equal to B plus C. So let's put both these values in this expression. So then X would become P. P is nothing but A bar. Note that P is nothing but A bar times, this dot denotes a multiply, times Q. Q is nothing but B plus C. And then finally we have this whole bar. So this is what it comes out to. Now this is what we have obtained, that for this complete circuit which has inputs A, B and C and these three logic gates, the output X we have obtained in terms of the inputs A, B and C, and the output X is related to A, B and C using this expression. Now coming back to the question, what we had obtained was that X is equal to A bar times B plus C whole bar. So X was A bar times B plus C whole bar. This is the expression for X. And we know that, yeah, so option B matches it exactly. So you know that's A bar dot B plus C whole bar, right? So option B is the correct one. Thank you for listening.